Good afternoon, everyone, and welcome, especially to those of you who are coming from colleges at various corners of Bangalore. Maybe some of you are here for the first time to ICTS for our event. So I hope this will not be the last. And you may know, I don't know whether you know what ICTS is. ICTS is, of course, a new institute, the International Center for Theoretical Sciences. We are part of the Tata Institute of Fundamental Research, and so in addition to our own research in various areas in theoretical physics, mathematics, quantitative biology, and related topics, we also have international events which bring together on particular research areas in these topics that I mentioned, which bring together communities of researchers from India and abroad to collaborate, for people to give mini lecture courses on advanced research topics. And if you're interested in seeing some of the topics, please visit our webpage and you'll see many of the upcoming programs. You'll also see many of our past programs, and you don't need to feel bad that you've missed them because you'll find most of the videos also on the webpage. And please subscribe to our YouTube channel, ICTS Talks, if you're not already a subscriber, because all the talks that are held here, they are available on this YouTube channel, and you'll get up-to-dates on the interesting lectures that are held here. But in addition to our research and these programs, outreach is a major component of our mandate, and we do hold a number of these public lectures, especially on when there are dramatic events in the scientific universe, like the present one, which is quite a spectacular story of how we've managed to image these black holes, and you'll hear from no better a person in India to hear it from than Professor Rajaram Nityananda. So we do events like this. We had a similar event when the LIGO discovery of gravitational waves was announced, and many other such events. There are other public lectures by eminent scientists from India and abroad. And so please stay in touch and come for these events. We also have lectures monthly at the planetarium. Perhaps you have heard of Copy with Curiosity. I'm just curious how many of you have heard of Copy with Curiosity. So I think we could do a lot more in terms of reaching out. That's a small fraction, I think. So Copy with Curiosity is a monthly series we have at the planetarium. The Nehru Planetarium in the center of the town. It's usually held on a Sunday afternoon, so there's one every month. And it's again a public lecture by a very good scientist. It's about, again, science in biology, physics, chemistry, mathematics, and accessible to members of the lay public. There's usually a very long question and answer session after the talk, and it's a very stimulating afternoon. If you attend any of these, you'll get hooked onto it. And once again, you can see the set of lectures on our webpage, the past lectures. So the next one in May is on the 24th, if I'm not mistaken. It's on complex systems. So please come if you can. And other than that, ICTS does the Einstein lectures in some of the colleges. Some of you are from PES, I believe. I think we've had some Einstein lectures there, and similarly with some of the other colleges in Bangalore. So a number of outreach events, and we hope to have a Bangalore area science hubba, or BASH, sometime in early 2020. Which will be like a festival for science, a hubba for science, and it will be somewhere in the center of town. This will be something with a lot of science institutions and others in Bangalore cooperating to come up with a novel science festival. So stay tuned for that as well. This is something that's in the works, and you'll hopefully hear more about it later. But that's enough from me at the moment. I'll now pass it on to Ajit. Professor Ajit heads our astrophysical relativity group here and was very much involved in the LIGO gravitational waves. So he will introduce the speaker, Professor Rajaram Nityananda.
Good afternoon. It's a great privilege to introduce today's speaker, Professor Rajaram Nityananda. Professor Nityananda is an outstanding physicist who has made pioneering contributions to different aspects of physics and astrophysics in very wide areas. He is currently a professor at the Azim Premji University. In his illustrious career that spanned almost 50 years, he has worked at the National Aeronautical Laboratory in Bengaluru, the Raman Research Institute, the TIFR's National Center for Radio Astronomy in Pune, the TIFR Center for Interdisciplinary Sciences in Hyderabad, and he also served as a director of the NCRA, the National Center for Radio Astronomy of the TIFR, as well as the TIFR Center for Interdisciplinary Sciences. So he's an elected fellow of all the major science academies of India, and he has made important contributions as the editor and the editorial member of a number of journals in India, including the Resonance, a popular science magazine which many of you are familiar with. Most importantly, he's an outstanding physicist and an amazing teacher, and I can guarantee you that you're all in for a treat. So without any further delay, let me invite Professor Nityananda to give the lecture.
Thank you, Ajit, for the kind introduction. My thanks to ICTS. It's interesting that I live in JP Nagar, which is some 50 kilometers away from here, and I get a chance to meet all of you so far in North Bangalore. There's been a lot of excitement about black holes. You heard from Rajesh about the event of 2016, where in some sense, we were able to listen to black holes because they emitted waves, not of sound, of course, but gravitational waves. And the event we are talking about today is that we are now seeing the black hole. Now, the black hole is defined as a surface from which nothing can emerge, not even light. So clearly you don't see such an object, which is why I have said unseen at last. And you'll see how the evidence for the black hole is not in any radiation we receive from it, but in the radiation that we do not receive from it. So let's go back to the 1780s, where two very bold thinkers, Michell, he was an English clergyman. Laplace, of course, is the famous mathematician, physicist, astronomer of France. So they both thought about an object from which the escape velocity would be greater than the speed of light, and therefore light could not escape. That was a kind of preliminary speculation about a black hole. You can see that I have just chosen the passage from John Michell. He was not a man of few words, but he was a man of few sentences. There's only one sentence here if you read it carefully. But he does say that even if we cannot see an object, we might be able to detect it from its influence on the surroundings, and that's exactly what's going to happen. Okay? That's exactly what has happened. Now, the very simple calculation they did, and I'm told the majority of the students here are from the pre-university, it's an ideal stage to be in, because you've just been taught all the physics concepts, and you have not had enough time to forget them. Okay? So, you cannot escape the concept of escape velocity. It's a standard interview question, exam question. There's the formula, mass in the numerator, radius in the denominator, right? So all that these gentlemen did was to say, let's put it equal to c. And then you find that if the radius is too small for a given mass, I've called it R minimum, and you can calculate that because you know Newton's constant, you know the velocity of light. So put in, say, the mass of the sun, and then you get a radius of 3 kilometers. Okay? Now the sun is much bigger than 3 kilometers. The escape velocity from its surface is much less than the speed of light. It's about 600 kilometers per second. Okay? But nevertheless, if you could pack the mass of the sun into a sphere of radius 3 kilometers, these people said light could not escape. But that is still a very classical conception. It's as if the light would go away and then come back. Okay? Now, you will see this long German name, Schwarzschild. And that's the name for the same formula. Accidentally, they hit upon the right formula. But this formula was given a proper meaning by Schwarzschild, who was an astronomer, a contemporary of Einstein. And Einstein created his theory of gravitation based on the curvature of space and time. He wrote down 10 really tough equations. The first person to actually solve them rigorously was Schwarzschild. And he arrived at a similar conclusion. Okay? So that's why we call it the Schwarzschild radius. This theme will keep coming up in the lectures. So just remember, mass of the sun, 3 kilometers. Now, this idea remained in astronomy, but was dormant. So meanwhile, let me explain to you something about M87, okay? M stands for a French astronomer, again around 1780, Charles Messier. And he searched the skies for fuzzy objects, objects which were not stars. And he had a very limited aim. His aim was he wanted to find comets. And if you see a fuzzy object, you think it's a comet. And then you have to wait and see it a few days later. And if it has not moved, then it's not a comet. And you wasted your time. So he made a list of all these fuzzy objects. These are modern photographs. So you see a lot of detail. This time, he just saw a blur. And he knew it was not a star. And the object we are interested in, is this one. Doesn't look very different from all the others. It's M87, 87th in the list. Okay? So let's take a closer look at M87. At the time of Messier, it wasn't known what they are. Okay? But many of these are actually galaxies. Right? The first example of a galaxy is the Milky Way. So when I came to Bangalore, you could see the Milky Way from Bangalore. You can't anymore because of light pollution. But you can, sometimes maybe the light can fail, electricity can fail, and then you can go out and see the Milky Way. Okay? It's our own galaxy. And Galileo was able to show it made up of stars. And in early 20th century, astronomers showed that even many of these were made up of stars. So here is a picture of M87. It's a galaxy. It has 10 times as many stars as the Milky Way. So what you call 1 trillion, or that's the same as a lakh crore, I think. Right? So actually more stars than our galaxy. Its shape is also different. The stars are distributed in 3 dimensions in a kind of spherical form. Lots of stars in the center. That's the bright thing which you see. And we will also be talking of length. So the standard unit which astronomers like is parsec. But the more familiar unit to many of us is the light year, the distance that light travels in 1 year. The two are closely connected. 1 parsec is about 3 light years. So the distance to the sun, for example, it only takes 8 minutes for the light to come from the sun to here. By the time you come to the outer parts of the solar system, it's more like 8 hours. So a light year is already like, several light years is the distance to the nearest star. By the time you come to our own galaxy, it's 50,000 light years. And M87 is much more than that, right? Yeah. 300,000 light years. But already early in the 20th century, people knew that there's something strange about this particular galaxy. And you can see this. This is definitely, these are stars, but this is not a star. It's some kind of line. And people didn't know what it was. They called it a jet, which means they were imagining that there's something here which is pushing some material out in this direction. But there was no further evidence on this. And the evidence came from a very unexpected source. It came from radio astronomy. And it's a bit of a surprise because light waves are quite small, half a micrometer. And radio waves are in meters, or the shortest radio waves are in millimeters. Right? And the longer the wavelength, then the more difficult it is to make a map with a lot of detail. Right? So now I will tell you a little bit about the optics of telescopes to make this point. Yeah. So here is a lens. Okay, and there's lots of rays falling on it. So concentrate on the blue line. You think of this as a wavefront all these rays are perpendicular to the wavefront, and then they all get bent. So in geometrical optics course, you're taught that they all come and focus here. But then you learn one more fact when you study wave optics, namely the total number of waves going from here to here is the same as the number of waves going from here to here. That may be a bit surprising because this looks a bit shorter than this. But please remember that this is traveling through glass where the wavelength is shorter. So it's quite an important fact that all the waves agree in phase. If one is a maximum, all the others are also a maximum, and that's why you get all this intensity at the focus. Okay? So that's fine as far as rays coming from this direction is concerned. But what if the rays come from a different direction? So I've drawn a slightly tilted wavefront. I haven't drawn the rays, that'll confuse the figure. But we know from our optics that should focus somewhere here. But the interesting question to ask is, would you still get some light here? Okay? Well, if these two make a very, very small angle with each other, then it could well be that the waves are perfectly in phase here, but even here they give you some intensity. Now, if that is true, your telescope will not be able to see these two objects as separate. So this is how we understand what is called the angular resolution or resolving power of a telescope. What's the smallest angle between two objects so that you see them as two objects and not as one? Okay? And from this figure, you can sort of figure out that if the tilt of this wavefront is such that the extra distance is of the order of a wavelength, then they would start cancelling here and you will get the image here. Okay? So, so what is this tilt? In radians, you take one wavelength here and this is the diameter of the lens. So this is the formula that we will be talking about. Wavelength divided by diameter of the lens, or lambda by d, is the minimum angle that you can see with a telescope. So you see the problem. Radio waves have a much longer wavelength. So how are you going to make fine pictures with radio waves? And the object we are talking about, M87, the finest astronomical picture ever made, was actually made with radio waves. Okay? And the answer, simple answer from this formula is you have to increase d. Now, how can you do that? You can't build a giant lens or a giant mirror for radio waves, right? But what you can do, this is the same figure, but a little more mathematics in it, right? If you ask what the lens does in terms of mathematics, it takes A, B, C, D, which are the waves falling on this aperture, right? And if you want to form an image of an object which is somewhere here, you can take A, you can also take B, but it's really you want to look at what B was here, not here. So even if these mathematical symbols don't make sense to you, think of this symbol as just B shifted here, and this is C shifted here, D shifted here. You have to add this up. Okay? And then the intensity you measure here is obtained by taking this electric field and squaring it. So algebra tells you that if you take A plus B plus C plus D, etc., whole squared, you will encounter things like A squared, B squared, and so on. But you will also encounter AB, AC, BD, etc. All right? So basically, what this tells you is that when a lens forms an image, it's taking the electric field, the waves which are entering the lens, and forming all possible products, and averaging them, of course. Okay? The word correlation is the technical word for multiplying these two waves, right? So keeping this in mind, radio astronomers started building telescopes, and so the one on the right was not the first one to be built, but it was one of the most powerful. It's called the Very Large Array. It is built in New Mexico. It has some 27 antennas. They are spread over 30 kilometers. Its wavelength, it was built in 1980. It goes from wavelengths of 1 meter to little less than a centimeter. Okay? But since you heard that I spent time at the National Center for Radio Astrophysics in Pune, in the year 2000, it's part of the Tata Institute of Fundamental Research, just like ICTS is. This group built, well, this was very large, and this was called GIANT, the Giant Meter Wave Radio Telescope, right? So even though it is not too much to do with our story, because its resolving power is not that high, I would still like to show this to you. These look very small, but they're actually 45 meters in size, And the only reason they look small is this was taken from a hill which was 6 kilometers. And you see maybe a 10 or 11 here, but there are 30 in all. So this principle of building up an image by having number of telescopes, taking the signals from them, and multiplying them in pairs, that's the fundamental principle behind the images that we are going to talk about. Okay? So it has a name. It's called aperture synthesis. Aperture is simply the entrance to the lens. Synthesis means that you don't have it all at once. You build it up. So, so in fact, you wait for a day or 12 hours because what happens is that these telescopes move to different positions as the Earth rotates. So this is the principle which was used. But so first, let me tell you what was learnt about M87. It turned out to be a strong source of radio waves. Okay? So now, for the next few slides, I'll be telling you the astronomical story of M87. Not at visible light. You saw the picture at visible light, but at radio waves. Okay? So I have the same, just to remind you, I've kept the same information here. The people who measured it in radio waves called it Virgo A. So they didn't know it is M87. There's a huge constellation of Virgo, and the radio waves were coming somewhere from that region. That was 1948. But gradually, as the telescopes got better and better, the pictures got better and better. So this is, most of these pictures are with the VLA. I'm sorry, this is a little smudged. Okay, right? So this is on the biggest scale, 25 kiloparsecs, of course, which is still small. Remember, the galaxy is 120 kiloparsecs, right? Very strange patterns of radio waves. Okay? Then, when they look, so this scale bar says 25. Now this is less than 1 kiloparsec. So they're looking at the inner region of this. Now you see this jet, which seems to be aligned to the same object which people had been puzzled by from the beginning of the 20th century, right? So it turned out that there is a jet. It seems to be emitting radio waves. And just looking at this picture, you would guess that, you know, there's something here which is sending out energy. Somehow that energy is giving you radio waves here. It's also interesting that it's giving you radio waves from here, but you don't see any jet connecting this to this. And the explanation which people came up with in the 1960s is, actually this is sending jets in both directions. One is coming towards you, one is going away from you. And because of the Doppler effect, which is also there in the pre-university curriculum, the one you normally hear, you're told that the frequency changes, but the intensity also changes. So you see this jet, but you don't see the counter jet. So the model which people came up with was that there is some source of energy here. Energy gets dumped here and radio waves come out. But as the telescopes improved, they zoomed in on this region. Okay? So this is now, and of course the wavelength is getting shorter and shorter, right? This is 1 meter, this is, I think, 20 centimeters, 3 centimeters. So you still see the jet. And this region was photographed by the Hubble Space Telescope. Same scale, a few hundred parsecs now, right? And this is revealed a dense concentration of stars. And the Hubble Space Telescope could do something which the radio people could not do. It could measure the velocities of these stars. And it suggested that these stars are orbiting around a massive central object, which is itself invisible. So since black holes were already known to astronomers, we are now sometime in the 1990s, when Hubble Space Telescope on the one hand and VLA on the other hand used these pictures. The movements of these stars suggested, and that gave an estimate of what could be the mass of this central unknown object. And the astrophysicists said, look, the best candidate is a black hole. So they came up with something like 1 billion solar masses. That's huge. Of course, it's still small compared to the mass of the whole galaxy. But it's 1 billion. So, but that is just a model. Now, if you calculate this radius of the black hole, it's still very, very much smaller than this. So the dream of radio astronomers was, can we keep building better and better radio telescopes so that we can zoom in right to the center here, right here. Not in the optical picture. The optical astronomers couldn't do it. So this is the first attempt. This is called VLBA, which is not just VLA, but adding more telescopes. But adding, these telescopes are 30 kilometers apart. So to add the signals, you basically send them over optical fibers to a common place. They're written down on a computer. You can apply these delays, which I told you about, and you can form your image. Okay? Now, by the time you put the telescopes hundreds or thousands of kilometers apart, you have to change the technology a little bit. Okay? So let's see, and these calculations were done sometime in the 1990s. Okay? What is the kind of angular resolution you need to see a million solar mass black hole sitting in the center of M87? So for that, I'd have to introduce some more units for really small angles. So just for comparison, the human eye has a resolution of about 1 arcminute. And that is equivalent to taking an object of about 1 centimeter and keeping it 36 meters away. That's pretty good, right? So when you go to the eye doctor, he asks you to look at a letter which may be only a few millimeters and maybe placed a few meters away. He's really testing whether your eye can resolve 1 arcminute. But then 1/60th of an arcminute is an arcsecond. But the convenient unit is actually radian, which I'm sure all of you are familiar with. So radian, you just take the size of that coin and divide it by the distance. So if I have a finger of 2 centimeters placed 60 centimeters away from me, it's just 1/30th of a radian, right? Divide the two. So we'll use radians, but people are also fond of arcseconds, so we'll have to. So arcsecond is a very small angle. It's 5 millionth of a radian, 10 minus 6, right? So keeping this in mind, that formula lambda over d we can evaluate. So I put the numbers for VLA, which is a single set of telescopes connected to each other, 3 centimeters and 30 kilometers, nicely chosen so that I think you get 10 minus 6 radian, which is less than an arcsecond. Right? So that is 16 parsecs at M87. So multiplied by 3, 50 light years. Now that's quite impressive because M87 is really far off. But will you be able to see the black hole? And the answer is no. We said 50 light years for the ability of this VLA radio telescope, which is one of the best ones, to see objects at M87, right? And what do you need? It's approximately 1 light day, right? A little bigger than our solar system. So what is the gap between 50 years and 1 day? It's a factor of 18,000. So you had to improve the angular resolution of the best radio telescope available in the 1990s by a factor of 18,000. Well, we have the formula lambda by d. So the biggest d that you can get on Earth is about 10,000 kilometers. Okay, diameter of the Earth is about 12,000. The shortest wavelength at which radio telescopes could operate is around 1 millimeter. Now, 1 millimeter is actually regarded as a very difficult frequency to operate. All the devices which you need, the oscillators, the amplifiers, and so on, become very high technology. Interestingly, in 1895, J.C. Bose actually created millimeter waves in his laboratory. He was a pioneer in that respect. And then the millimeter technology was forgotten. Radio waves went to long wavelengths. And then a century later, or half a century later, people came back to millimeter waves for a different reason. Not to get high resolution, but to study interstellar molecules, okay, which is another story. So a lot of telescopes operating at millimeter waves had been set up all over the world to study interstellar molecules. They're very interesting. You can study water, H2O, carbon monoxide, many of them. In fact, there was a millimeter wave telescope at the Raman Research Institute where I used to work. These telescopes can only operate in good weather because the atmosphere, even a single cloud will absorb those millimeter waves. So, around the 1990s, a couple of people got together and said, look, we have to do this. So let's go to all these existing millimeter wave telescopes and let us equip them with the best equipment, and we will record the radio signals. We can't combine them. We can't lay optical fibers connecting all these telescopes. We'll record the signals and play them back. So that's a technology which had already been developed. So this is still our old lens. It's adding up waves, but it's a I would say the waves are being added offline. You record each wave at A, B, C, D in that old figure. And then, so it's called VLBI, a very long baseline interferometry. Interferometry because you're adding the waves and seeing whether they are in phase or out of phase. They are widely separated telescopes, and widely separated could be thousands of kilometers. But you have to now compare them. How can you compare these waves which you have recorded in very different places? You need very accurate clocks at these places. And thanks to the GPS, the time at these places is now can be set to an accuracy of a few nanoseconds. But you also have to keep track of the wavelength, right? So the wavelength which is used for the experiment which I'm going to describe, produce this black hole image, was 1.3 millimeters. So if you ask what's the time period between two of these waves arriving, first crest and second crest arriving at the telescope, it's only 4.3 picoseconds, 10 minus 12. Okay? So you have to record these, right? I mean, all of you are used to have kbps and mbps. So each of these telescopes records data at 32 gigabytes per second, right? And it records it for hours. So no question of sending this over an optical fiber. And you'll see that these telescopes are all in very remote locations. So all these hard disks on which it's recorded, and of course you must record the time at which you did the experiment. And then these are sent by plane or by post. It was two central places. By this time the collaboration was across the Atlantic Ocean. There was a strong group in Germany, a strong group in the United States. And just to make sure that there was no mistake, independently these two groups processed these tapes. It's a very tedious process. So it's easy for me to show you a slide saying take A plus B plus CD whole squared. In practice, all these time signals, all these tapes had to be played back. They had to be aligned with each other. To some extent, there's an element of trial and error in it. Okay? So that is very long baseline interferometry, which had not really been done at millimeter wavelengths. So these pioneers first showed that it could work at millimeter wavelengths, and then they planned grand. Now, it didn't happen in one jump. Okay? So this is at 86 gigahertz. Now, gigahertz is, so that's a wavelength of about little more than 3 millimeters. Interestingly, the RRI telescope could also work at this frequency, but it was a single telescope, it's not connected. And interestingly, J.C. Bose was already working at 60 gigahertz. So just think of what a pioneer he was. Okay. So this is now zooming in still further, but before the EHT image. I should tell you what EHT is. So still, we realized that yes, this is the jet probably been launched from here, but this still looked like a blob of emission. The reason is that if you look here, it's 0.2 milliarc second, so that's very good. But it's still 28 times this Schwarzschild radius, which is the size of the black hole. So the size of this blob is still 28 times the kind of size that you would like to see. But this was really a trial to see whether the technology could work. Worked. But they realized that, so the detail, the resolving power in this telescope is about 3000. I have changed the units again, apologies for that. Parsec is too big a unit, light year is too big. So now it's in astronomical units, which is the radius of the Earth's orbit, which is 8 minutes. Okay? So here they are seeing an object 3000 AU in size, but they were looking for an object a few hundred AU in size, so they had to do better. Now EHT stands for Event Horizon Telescope. Okay, I'll be telling you more about black holes in the latter part of the lecture. But basically, if you have a surface from which light cannot emerge, then whatever is beyond that surface is inaccessible to you. So you cannot see events beyond that telescope, very much as on Earth you cannot see objects beyond the horizon. So that surface is called the event horizon, and this collaboration called themselves Event Horizon Telescope, okay? EHT. So to give you a feel, this is taken from the website of the German side of the partnership, Max Planck Institute of Radio Astronomy. So now you can see this is truly, I mean, people talk of globalization, but this is truly on a global scale. So here are the telescopes which were combined. You see pictures of the telescopes themselves. Each one of them is interesting in its own right, and all of them were built for a different purpose. So the people who proposed this project had to persuade people in different countries, different observatories, saying, give us this time, we'll give you all this equipment, and we will achieve this great goal. Okay? So here is a telescope in Hawaii, which is, I think, Chile. Chile actually already had a major set of telescopes, not just one. Okay? This is the telescope in Chile, right? This one is in Hawaii, I think. This is Mexico. There's even one in Spain. And imagine that you are M87. Just, as the Earth rotates, the one in Spain will rise just as the one in Hawaii will set. Okay? So this is a very, you may get only a few minutes in which you can see both. And interestingly, they had one telescope on the South Pole. I think that's this one. Okay? Yeah, it is definitely this one. Why it's interesting is M87 is actually north of the equator. So it cannot see, the South Pole telescope cannot see M87. So, however, whenever you do such an observation, you also have to do calibration. You have to point the telescope to some other source. So when you point it to a southern source, the South Pole telescope is very useful. And basically, if you think of all these clocks, you have to synchronize all the clocks. And one way of synchronizing it is to point it to a known source. Okay? So that's these telescopes. And this is the image which has made all the news. And now this finally has the angular resolution. So this is the unseen part that I told you about in the title of the talk. This is what you see. Now, this is what you expect from a black hole. So meanwhile, theorists had not been idle. Okay? So let's go back. I told you that Schwarzschild gave an exact mathematical solution, Einstein's equations. It seemed to show that something interesting is happening at this radius, but one of the peculiarities of Einstein's equations is the same physical situation can be described in many ways. And some of them may bring out the physics more clearly than others. I think it took almost 40 years after Schwarzschild to really figure out that this surface was acting as a one-way membrane. So before we leave Event Horizon Telescope, I told you that it's like a lens, but it's not a perfect lens, right? Because these telescopes don't fill the whole Earth. Even if you observe for some time, so you should think of Event Horizon Telescope as a lens where these colored parts are the parts where the lens is letting through light. So clearly, forming the image is not going to be very simple. I'll come back to that later. When I was preparing this lecture, and I had this interesting task of explaining the general theory of relativity in maybe 10 minutes or something like that, I decided that, see, it's one thing to learn the mathematics of general relativity. And especially when you're young, after my MSc or early in my PhD, saw the equations, you sat, you worked them out, and you thought you had understood general relativity. But it's only when I joined the Raman Institute, where there were real people working in general relativity, my field was optics and condensed matter physics, a little different. And one of them was Professor C.V. Visveshwara, who passed away recently. And he wrote this marvelous article for the Einstein Centenary, which was 1979. I'm putting it up, first of all, so that I can borrow the figures, which he drew himself. Okay? And in some ways, if you read the text of the article, it will actually tell you technically correct things about black holes, but also with a very light-hearted touch. And so what is this surface at the Schwarzschild radius? The modern understanding is that it is indeed light, which is trying to travel outwards. Remember, Laplace and Michell said the light would travel outwards and fall back. But they were wrong. What general relativity tells you is the light is traveling outwards, but the radius of this wavefront remains the same. Now, that might seem a little strange, right? Why is light not moving at the velocity of light? well, after all, the same Einstein told you that, any observer will see light moving at a speed c. But the catch is this. From a distance, you see the sphere as having a constant radius, and it looks like the light is not moving. But Einstein told you, go there and measure it. Okay? So then what happens? If you go there, you fall in through the surface. So as far as you are concerned, this surface will actually appear to be traveling outwards at the speed of light. And that's what Professor Vishweshwara has illustrated in this figure with his inimitable humor. So the wavefront crosses you, right? But then you can never catch up with it again, okay? And this diagram illustrates it more. So this is the x-axis, which is space. This is the time axis. And please imagine one more axis pointing towards you, which is the y-axis. And so this, you choose proper units, like suppose t is in years and x is in light years, then the speed of light is 1 light year per year. So it's a line at 45 degrees. And if you include the y-axis, it's a cone. And since you move less than the speed of light, you are trapped inside this cone. That's the essence of special relativity, which is captured in this figure. But that's special relativity, which works locally in a small region. Now, the black hole is really this frozen wavefront. Okay? I mean, that's, at least with my kind of optics orientation, that's the best explanation I can give you about the black hole. But we actually have to go a step further. So it's as if, I think, okay, one more analogy, if that helps. Okay? Suppose there's an escalator which is traveling down. Some of you may have tried to run up, right? So you may be running as far as the escalator is concerned, right? And you may be thinking you're running. But as far as someone looking from far away is concerned, you're just standing still, because as you run up, the escalator drags you down. So in fact, the analogy given in this article, in fact, he invokes the writings of Lewis Carroll. I don't know how many, it's not fashionable to read Alice in Wonderland nowadays. But how many of you have read Alice in Wonderland or seen it? Okay, a reasonable number. So here's a famous quote from it. The Red Queen says, "It takes all the running you can do to keep in the same place." Right? And that is, he has used this analogy to explain what's happening at the horizon of a non-rotating black hole. All astronomical objects rotate. It's expected that the black hole at the center of M87 is no exception. So the rotating black hole comes with an extra twist, which is explained in this figure. Okay? Again, inimitable cartoon. And if you read the words, the rotating black hole is like a whirlpool. It sets up currents in space-time. And therefore, if you do nothing, you will be carried along with it. But if you don't want to rotate around it, you actually have to drive an engine or something like that. So anyway, that's your brief introduction to black holes. And I think this article is available on the web. I urge you to. So how do black holes help in explaining these strange phenomena which astronomers have found at the center of M87, but also at the center of thousands of other galaxies? And there is some universal aspect to these phenomena. You see these jets. Sometimes you see a lot of visible or ultraviolet or X-ray radiation as well. And if you have these jets, you also see radio waves. So physical process which is brought in by astrophysicists to explain this huge release of energy goes by the name of accretion. Accretion is matter falling onto any central object. And this is, if the matter falls straight into the black hole, it doesn't have much time to radiate any energy or to do anything much. Okay? But fortunately, it appears that this is a somewhat rare case, what is called spherical accretion, matter falling in from all directions. What is more common is that the infalling matter comes with some angular momentum. So that means it's really orbiting around the black hole. So it spends a lot of time there. Now, every orbit has a certain amount of energy. And as the orbit shrinks, it goes to lower and lower energy, which means a certain amount of energy is released. Now, nowadays you often read that if you have a spacecraft, right, and the Earth's atmosphere exerts a force on it in the opposite direction to its motion, a drag force, this removes angular momentum and this object will spiral in and crash somewhere. Every now and then you hear that. But fortunately, most of these small pieces burn out before they reach the Earth. Okay? So this is an example of an orbiting object shrinking its orbit because angular momentum is being removed and coming to lower and lower energy. And where does that energy go? It needs some kind of friction, right, to bring it down. So it goes in the form of heat. So basically, that is the principle which is being used by astrophysicists to explain the energy being released in the centers of these black holes. They say that you have gas falling in. The gas is in orbits. And these orbits around black holes differ in an important way from the orbits as calculated by Newton's laws, which we are all familiar with. Far away, of course, is not very different. But I mentioned this short shield radius, RS, okay, which is about 1 light day for M87. Now, already at 3 times this RS, the orbit becomes unstable, which means, yes, if you put it there and you give it exactly the right velocity, it will go in a circular orbit. But any deviation, and it could fall into the black hole. So this is called innermost stable circular orbit, ISCO, affectionately known in the black hole trade as ISCO. Okay? So basically, the gas can spiral in up to this ISCO, and it releases about 10% of its rest mass energy. That's a huge amount. So just to give you an idea of how powerful rest mass energy is, the entire Hiroshima atomic bomb corresponded to the release of the rest mass energy of just 1 gram of matter. Okay? So getting 10% of the rest mass energy is a pretty impressive amount of energy. And astrophysicists were able to use this. At least they could do the accountancy, saying so much energy is coming out. But is it coming out in the right form? Is it coming out in a jet? Right? So they had to put more things into the model. So because of this friction, which I will explain, the gas becomes very hot. But interestingly, another thing happens. When the gas becomes very hot, the electrons get separated from the nuclei. So it becomes an electrical conductor. And let's say you have a tiny amount of magnetic field, and you have this electrical conductor going round and round, then it's a dynamo. Okay? So that will set up currents, which will set up more magnetic fields, right? Which will set up more currents, right? So basically, any magnetic field put into this rotating, orbiting gas gets amplified. And this is important because, for one thing, the magnetic field is like a rope. It connects different parts of this infalling gas. So it allows one part of the gas to communicate with another part of the gas. It also, some of the magnetic field lines travel away from this orbiting gas disk. And because it's rotating rapidly, their centrifugal force throws some matter out along this. So at some level, people were able to explain these jets based on this model of having a magnetic field. Actually, this is similar to what is happening in Bangalore, or 1,000 feet below the surface in Bangalore. You have pumps which pump water up. And if you go down and see, many of them are centrifugal pumps. You have a rapidly rotating set of blades, and the water goes in, and then the centrifugal force pushes it all the way up to your house. Okay? So in some sense, the model which was developed, I'm just describing it in words, is that you have this accretion disk where matter is going round and round. It's also, of course, you need an energy source, and that energy is gravity. As the matter falls, it loses potential energy, converted to other forms. And it explains the jets. It could explain magnetic field. Once you have magnetic field and charged particles, you can have radio waves. So this model was first built up very qualitatively, but today it's a very quantitative model. People can put all these equations into computers. The computers are getting better and better. And of course, it's still, they have to adjust the computations based on the observations. But people are able to explain what's happening in M87, assuming that there is a black hole at the center. So you can see that astrophysicists already put all their money on black holes. Okay? There were a few people who thought maybe other kinds of objects could be there, but majority. But once you put all your money in some bank, you don't want that bank to fail. Right? And therefore, everyone is waiting. Now, this friction is a slightly subtle thing. I just like to, because it's a nice piece of physics. You can have a spacecraft spiraling and crashing on Earth because of the friction of the atmosphere. But there's no atmosphere around the black hole. So what does friction do here? So I've just drawn this picture of two rings of gas orbiting around the black hole. And the one which is further away orbits at a lower speed, right? That you can work out from standard physics. V square falls off as 1/r. But now, interestingly, because they're moving at different speeds, they rub against each other. So the inner one, right, is moving faster, it gets dragged, it experiences the force backwards. Whereas the outer one, which is moving slower, experiences the force forwards. So what happens then? So the inner one travels inwards because you're extracting its angular momentum, and the outer one, you're giving it angular momentum, it's pushed outwards. So two gas rings can exchange angular momentum. So without any external medium, at least the inner part of the disk can spiral in. But for that, you need to push something out. So that's just an interesting piece of physics, which I thought I'd point out to you. I also find it ironic that people found various sources of energy over chemical energy, nuclear energy. Now, you come across the most energetic objects in the universe, we are back to rubbing two sticks against each other. Okay, I told you about the orbits of particles. But these particles emit some radiation, and the radiation reaches you, and the radiation is passing this massive object. So we also have to understand the behavior of radiation. Let's call it photons, particles. So what are the orbits of photons? And this is something where Newtonian theory is silent, not meant to deal with photons. But Einstein's theory gives a very definite answer. So for simplicity, I have taken a non-rotating black hole, which is, so this is the event horizon where you go in, you don't come out. This is some part of this accretion disk, which is emitting radiation, right? If the radiation passes a little far away from the black hole, it's bent, goes off. So in fact, I've shown this radiation, which would have got spread over a very wide area, because bending by the black hole has actually all come and reached you. This effect is sometimes called gravitational lensing. So you can well imagine that if you have material near the black hole, you will see it as a ring. I mean, in this figure, it's 2 points, but if you rotate the figure about this axis, it'll be a ring. But what about things which are emitted here? They just go crash into the black hole. So they don't reach you. So that's the reason why I said the black hole is unseen. Now, one good way to understand this is that in the proper, when you work it out for black holes, for photons, there is a unique orbit, but it's an unstable circular orbit. So I decided for this lecture at least, since that was ISCO, I'll call it USCO, USC. Okay? So this is the unstable circular orbit. And what does that mean? That if something is moving in this direction, you disturb it slightly, it'll crash into the black hole. Or you disturb it the other way, it'll escape to infinity. So all these properties were known for a long time, but what has happened as the interest in the astrophysics of black holes has increased is that these have all got into the computer codes. So this Event Horizon Telescope collaboration, of course, they did it in a very dramatic fashion. I mean, there were rumors going around that they're getting interesting results, but they did not want to publish half-baked results. So they kept everything within the family. It's a very large family, 300 authors. It's still small, I guess, compared to the teams which worked on LIGO or worked on some of the particle physics experiments. From 100 institutions. I mean, these numbers are rough because I got a little tired of counting when I read the paper. But I did notice, naturally, being from India, you look for names of PIOs, persons of Indian origin. I counted 13, of whom 4 were actually PBOs, persons of Bangalore origin. And one of them, Ramesh Narayan, was a colleague at the Raman Research Institute, now in Harvard. He worked, even when he was at the Raman Institute, in areas, exactly the areas which happened to be relevant to this problem. So he was very well prepared. Gravitational lensing, accretion onto black holes. And the last part, about which I will not be able to tell you very much, namely, if you form an image with a bad lens, where lots of the light rays are missing, or lots of the waves are missing, how can you still get back the original image? Okay? So these are all the technologies that went in. Of course, Ramesh was by no means the only one. Many well-known astrophysicists were members of this collaboration. And interestingly, the number of people of Indian origin were so large that they were in duplication of names. Some of the others, okay, let me. So I have also mentioned names of 2 people, which may be a little unfair when it's a collaboration of 300 people. But if you look at the literature before that, these were the people who saw that this was possible, and they wrote papers on it. And more important, they went around persuading these observatories, got the funding for the equipment, went and tested that it all works. BLB experiment is, if even one observatory fails, you're in trouble. You can't say the clock didn't work. And something has to work at the South Pole, something has to work in Spain. It's an experiment on a grand scale. Okay? So I would say that they took all the existing technologies of radio astronomy and computation and stretched them to the limits. So, this is the end of the field? Not really. For one thing, I've just mentioned overall results, but there are 6 scientific papers which came out. Right? The first one gives the overall summary, and then in detail, like modeling the accretion disk, or modeling the bending of light, or how do you make sure that the data is correct. Each one of these is a paper of about 40 pages. Okay? Makes very fascinating reading. In particular, I'd like to mention, apart from Ramesh, 2 other people who did their PhDs on the millimeter telescope in the Raman Institute. And then they joined one of these groups in Hawaii. And they're also authors on the paper. One of them is actually setting up a telescope in Greenland. So they're not satisfied with only the South Pole. They want something near the North Pole. And the idea is that they won't stop here. They will get better data on M87. The center of our own galaxy, you may say, look, why are you, charity begins at home. Why are you looking at this galaxy, which is 16 million light years, 50 million light years away? Why aren't you looking at something which is just 10,000 light years, 30,000 light years away, right? Our own galaxy. The answer is, our own galaxy has a very tiny black hole, 6 million, not billion. So even though it's closer, the angle is, and there are some technical difficulties with observing it, but they have promised that they will give us an image of that, and there are other objects. The next step has to be to put the antennas in space. You can reduce lambda, but you have to increase d. Now, VLBI has already been done from space, but not at millimeter wavelengths. So I've mentioned the names of the 2 Raman Institute colleagues, and I've been talking to one of them, and he says the group in Hawaii is prepared to share information and technology if there are groups in India who want to put one in Ladakh, because it's you need a high place where there's not much water vapor above, and it really helps to have the antennas spread out over the world as much as possible. I'm just mentioning this because I recently happened to have a talk. So this ring around the black hole, on the one hand, it's the end of a very long quest. In fact, I wrote a small blog piece which is about to come out, where I compared these 2 gentlemen to this captain in this novel called Moby Dick. His whole life's mission is to find a white whale. So I don't know about the entire life, but at least from 1990s, their mission has been to find black hole. To actually, so now this part of the story is over, but some new story will begin. There are more galaxies to be studied, and getting better and better data on the existing one, constructing better and better models will continue. So the excitement about this discovery is not, when you read about something in the papers, you think that it just happened overnight. It did not happen overnight. There's a very long history, and it's not the end. We are going to see more developments in this field of imaging black holes. And right now, it does appear that the best tool available to us, using very short radio waves of the kind pioneered by J.C. Bose, and spreading the antennas all over the Earth. Okay? Thank you.
Thank you very much, Professor Nityananda, for this wonderful lecture. So he will take some questions. Before we start, let me ask Professor Bala here to hand over a small memento showing our appreciation.
Thanks, Bala. Glad you liked it.
Thank you, Bala. So if you have a question, please raise your hands. One of our volunteers will bring a mic. Please try to be very short and precise. Ask questions.
So thanks for that wonderful lecture. We have found a great deal of evidences for black holes and all that. So when would we like find evidence for a white hole? This might seem a bit fictional, but get the point.
Yeah, so the question, which maybe all of you heard, is there is a theoretical concept, which is a white hole, which is in some sense the reverse of a black hole. So it's a surface where you cannot get in, but various things will come out. Okay? Now, no one knows how to create such a surface. At a very loose level, you could say the origin of the universe is something like that. I mean, we are seeing things coming out from the Big Bang. We don't know how, and you can't go back in. Okay? It's in the past. Right? But I think you're probably thinking of a discrete object, which is the white hole. Now, one of the technical problems, of course, in astronomy, you should never rule anything out. Okay? And indeed, many distinguished astrophysicists have speculated on white holes. Curiously, all their names begin with N. Narlikar, Novikov, and Neyman. I remember. But this was perhaps many decades ago, where the properties of some of these strange astronomical objects were unexplained by other models. So it was very sensible to consider all possible models. Currently, it looks as if the black hole models are succeeding. One cannot rule out that some different class of astronomical object, which is not known at the present time, might show these characteristics. So that's the best answer I can give you. That what people have to do is to work out the properties. And there is a small technical problem that in the case of the black hole, you know how it might form. You take a star, and then maybe the pressure in it decreases because it has run out of nuclear fuel, and it collapses. So that's something you can follow on the computer, because we are used to what we call in physics as the initial value problem. You give me some data, and let's go into the future. Right? In the case of the white hole, because it's the kind of reverse, we don't know what are the initial conditions from which it came. But that doesn't rule it out.
Form of Hawking radiation. Right. So would it be ever possible to sort of measure that and get maybe another picture of another, let's say, of a black hole in the form of Hawking radiation?
Okay, thanks for asking that question. So that's one topic which I omitted. Now, indeed, how many of you have read or at least held in your hands or looked at a book by Stephen Hawking called Brief History of Time? Yes. All students I know have looked at this book. And one of the chapters in it is called Black Holes Ain't Black Anymore. Okay? And it's true. In 1974, he worked out a theory, which is widely accepted today, that if you include quantum mechanics, which we did not include, then this radiation comes out, which is known by his name, Hawking radiation. But for our purpose, it's not important, because this radiation actually keeps increasing as you consider black holes of smaller and smaller mass. So for the black holes formed by a single collapsing star, or the black holes which form in the centers of galaxies, and we don't know how they formed, could be many smaller black holes assembling and so on. Hawking radiation is negligible. Okay? However, astronomers have considered, suppose, see, as I said, the Big Bang is a bit we don't know what are the conditions. What could have been created in the Big Bang? Suppose it created a number of small black holes. And some of those would be emitting Hawking radiation, and is it possible to detect it? Now, long ago, a very famous astrophysicist, Martin Rees, wrote an interesting paper saying, suppose there's a black hole which emits Hawking radiation, comes to smaller and smaller mass and explodes. And it explodes in a region of space which has a magnetic field. Then you would be pushing a conducting material into a magnetic field, and your 12th standard physics tells you that it will produce a current. The current will produce electromagnetic waves. So he predicted. People have looked, because again, as I said, in astrophysics, you shouldn't rule out anything. So if we had these mini black holes which were evaporating by the Hawking process, one signature might be seeing these pulses of radio waves. They have not been seen so far, but who knows?
You would observe them as
Yeah, radio wave seems to be the best tool for looking for this, exploding black holes.
Black hole in M87 is last photon stage, as I've said, is in its last photon stage. The black hole which I've found in M87.
No, I know.
Yeah.
I know. But
So-
what did you mean by last photon stage? Maybe I
That's what I wanted
said
to
something.
ask you, sir.
Oh, okay. Ah, sorry. All right. No, the black hole is doing fine. Okay. But if you consider a photon, first of all, no, there are two things. If you consider a material particle, it can orbit in a circular orbit anywhere from infinity up to this ISCO. Now, a photon is different. There's only one orbit allowed for it, which is at 1.5 times the Schwarzschild radius for a non-rotating black hole. So it's not the last circular orbit, it's the only circular orbit for photons. In the case of material particles, the gas which is coming in, it's the last orbit. And after that, it plunges in very quickly. So, sorry, maybe I didn't say it clearly enough.
Yeah, thank you for that wonderful lecture. I mean, there is kind of speculation, or not speculation, as in theories going on as to which came in first, whether the black hole came in and the galaxy formed around it, or the stars got together and formed a black hole together.
Yes, actually, I should mention that there was a time when it was big news if a black hole was discovered in the center of a galaxy. Today, if you found a galaxy without a black hole in the center, then that would be a big news item. Because it looks, but all of them don't emit these jets and radiation. The reason is that they don't have any gas or stars falling into them, okay? So black holes in the centers of galaxy are a very universal phenomenon, and that raises this precise problem. My impression from the astrophysics literature is people would like to form stars. The stars would then, some of them, see, the early stars could have been very different from the stars we see today. In particular, it's believed from some modeling that they could, currently stars go to about 60 times the mass of the sun. Okay? But maybe those early stars could go to 1,000 times the mass of the sun. So they could quickly form, and their lifetime is very short, and they would form black holes. And then these black holes could merge. So that's the scenario in which the stars come first. Now, if these fail, then we are left with the other option, which you mentioned, that the black holes have to exist before stars. Then they have to come out of the Big Bang. And Big Bang is, you can, it's up to you. Of course, such a theory also has to be tested. But current theories of, the early phase of the universe seem to show fairly uniform distribution of matter, not concentrating into black holes. But it's not tested. At those small scales, perhaps black holes could form in the early universe, but we don't have any mechanism.
Right now, whatever galaxies we have imaged, so every galaxy has got a supermassive black hole at its.
I mean,
So that has to be there to make sense.
I don't know, has to be there because it has to form. It looks like the galaxy formation process itself allows a lot of gas to accumulate in the center, form some massive stars. But yeah, this is an open question. And in fact, typically this black hole has a few % of the mass of that central region. So yeah, that's one of the currently hot topics in astrophysics. You're perfectly right.
Good evening, sir. My name is Sanket and I come from DCFLPU College. And my question to you is, there is presence of antimatter in this universe. So if we possibly could, shoot antimatter inside of a black hole, we could annihilate the gravitational intensity of the black hole, or we could possibly kill a black hole. Is it possible?
Okay. Now it's true that as far as certain properties like charge is concerned, antimatter can annihilate matter. Right? Now, a black hole can, in principle, have charge. Okay? Though such black holes have not been detected, Einstein's theory allows charged black holes. So if a black hole has some charge and you put in the opposite charge, the charge on the black hole would reduce. Okay? However, this would not annihilate the black hole. The mass of the black hole would increase and the area of the surface would increase. So, so the answer is that, in fact, it's very hard to, the only mechanism we know to annihilate a black hole is Hawking radiation. Okay? And that also doesn't work for very massive black holes. The time taken for the mass to decrease by Hawking radiation is far greater than the age of the universe. Meanwhile, they are actually collecting matter from the surroundings. So yeah, at the moment, we don't know how to annihilate black holes.
Thank you, sir.
I wanted to ask a simple question. You have shown us that whatever we are seeing on the picture is actually all radio waves collected all over the world. How do you convert those radio wave pictures to a visible picture?
Okay.
Papers, what come is a visible picture.
Okay, fair enough. I think somewhere in fine print they say this is false color. Okay. So basically what the computation tells you is the intensity of the radio waves. Then you can just run a computer program which says if the intensity, in fact, I think some of those pictures even had a scale. So the quantity which was actually being represented on that ring was what radio astronomers call brightness temperature. That is, and it was about 1 billion degrees or something in the brightest part of the ring. Okay? All that means is the radio waves are at 1.3 millimeters, and the intensity of the radio waves is such that as much as would come from a body at 1 billion degrees or something like that. So it's just a conversion to color for visual representation. I should have said that. Thank you for pointing it out.
What will happen if two black holes come together?
They become one. I mean,
Collapse.
that is the event which happened in 2016, around which there was a major meeting here. So if you want it in the form of dialogue of a film, हम दो से एक बन रहे हैं. इन तरफ दो से तीन बन रहे हैं.
So can a black hole be destroyed?
I think it's related to the other question. According to the physics that we have right now, the only mechanism which seems to reduce the mass of the black hole is Hawking radiation. And what happens after that is hotly debated amongst theoretical physicists, and many of whom are in the audience. Maybe one of them should tell us what take the mic and tell us what the current thinking is. But apart from that, if you do other things like merging black holes and so on, they just get bigger and bigger.
Can it be exploded? Like it contains so many mass in it, so can it explode at any point of time?
Except for this quantum process, general relativity forbids any material from coming out of this surface. It is not allowed because that material will have to move faster than light as measured by a local observer. So I showed that picture, that the wavefront can cross the observer, but after that the observer cannot catch up with the wavefront. So as I said, based on our current classical picture of black holes, the answer is no. But there are people, including I think people in ICTS who are questioning that picture, right? Who are saying maybe our understanding of the interior of the black hole is incomplete and we have to bring in quantum physics. So that's why I very safely stayed outside the black hole. I didn't want to fall in. No, it's a good question.
I have a question, sir. Are black holes or doorways to other parts of the universe?
Okay. I think, let me tell you my understanding of this. Einstein himself, along with a collaborator called Rosen, came up with one of the solutions of the equation, which had, pictorially it was a flat thing, and then it became narrower and narrower, and then it became broader and broader again. And I think, so today this is called a wormhole. Okay? However, again, using what we know of general relativity, this wormhole lasts only for one instant of time. And then again, there's a lot of interesting literature in relativity asking, can a particle get through this wormhole, right? And the answer seems to be no. But the moment you bring in quantum physics, all bets are off, at least as far as I understand it.
Thank you, sir.
Good afternoon, sir. Sir.
Yeah.
Sir, what is the importance of black holes, sir?
From the point of view of astronomy, which is what I'm concerned, they seem to explain phenomena which was very difficult to understand from any other model. In fact, that original quote by this English clergyman said exactly that.
Sir.
So basically, it's a model for astrophysical phenomena, and typically they tend to be energetic phenomena, which is actually a little bit of a paradox, right? That black hole swallows everything, and then when you see something coming out of that region, you say, oh my God, there must be a black hole. That sounds strange, right? But I hope that all the account I gave you of how the matter spirals into the black hole, throws out material by centrifugal force, creates magnetic fields, explains how the black hole can both swallow matter and emit energy. And there are certain objects, and very compact objects, which are emitting a huge amount of energy. And of course, the ultimate example is this recent merger, which we observed in 2016 of two black holes, and the amount of energy emitted in that was huge, right? And in a very short period of time. So I would say that sometimes in politics, they have this thing, no credible alternative. So that is the use of black holes. When you have situations where there is no credible alternative, but actually it's better than the politics because this alternative is becoming more and more credible as more and more observational evidence is being gathered and as the theoretical modeling gets better and better.
Sir, one more question.
Yeah.
Sir, does time travel slow near the black hole?
In some sense, yes. Yes. There is, if you sit at infinity, and this was something which was done in 1930s by Oppenheimer and his student, and it's quite famous, that they worked out if you have this matter collapsing to form a black hole, but they only viewed it as viewed at infinity. So in their picture, it slows down and it never actually reaches that surface. Okay? So in fact, in the Russian literature, black hole is called a frozen star because of this paper by Oppenheimer. It seems to slow down. But if you were sitting on that matter and falling in, it would all happen in a finite time. So there is this conversion between the time as seen by a freely falling observer and the time as seen by an observer at infinity. And the observer at infinity sees this process slow down. You're perfectly right here.
Thank you for your lecture, sir. I have a question. You spoke about ideal cases of non-spinning black holes. So what happens in the case of spinning black holes? What all different complications and parameters do you consider when it's a spinning black hole, and what all changes in terms of Schwarzschild radius like that?
Yes, things do change. It's only for simplicity that I omitted the spinning black hole, though I mentioned it briefly by showing the picture from Visheshwara's article. All the modeling which has gone into these 6 papers includes the spin of the black hole. The most remarkable thing which happens in a spinning black hole was discovered by Roger Penrose. There is this horizon, the surface, where if you enter, you cannot leave. Okay? But surrounding that horizon is another region where you could enter, but you can't stay still. You have to orbit. You can't just stand still there, even if you have a rocket of infinite power. So there is this region called ergosphere, and what Penrose showed is that in principle, you can extract the spin energy of this black hole by getting into this region and coming out again. And when I made some very general remarks about magnetic fields, one of the important processes which has been put into these computer models is that when the magnetic field enters this region, it's able to extract energy from the spin of the black hole. So one dynamo I mentioned was in the gas outside, but there's another dynamo which can function in this region. So spinning black holes have this new feature of what is called ergosphere. And what I do want to say is that all the current work includes, and they even try to find out what is the spin of this black hole. So.
Good evening, sir. Sir, is it possible to create black holes here on Earth? And if it is possible, what will be the consequences? Like the rumors going on, like they create black holes using LHC.
Okay. See, the black hole does give you a formula. I mean, the simplest formula, which is on the very first slide, tells you how much energy you have to put into what volume to create a black hole. To the best of my knowledge, no human accelerator does that. You may be remembering something else which was stated, that the LHC might create some new form of vacuum, which would then expand, and but that is really different from black holes. Yeah, I think for black holes the numbers don't work out.
Good evening, sir. My question is, how big or how small can a black hole get? Does it have a size? Does it have a size limit? It should be this big to actually become a black hole.
Okay. Once you have formed a black hole, its radius simply is proportional to the mass. Okay? But maybe, was that your question? At the bottom end, for very small black holes, quantum mechanics may be setting a limit, which is actually an interesting mass, about some 10 to the minus 5 grams or something, or 10 to the minus 8 kilograms. I mean, but on the upper end, the biggest which has actually been observed is probably M87, or maybe there are a few which are more. In fact, it's interesting that it's, again, an astrophysicist of Indian origin who right now is writing the maximum number of papers trying to find the most massive black hole. Her name is Premji Natarajan at Yale University. But theoretically, I don't think there's an upper limit. Of course, I mean, it shouldn't take in the whole universe, right? In that sense, yes. But otherwise, I'm not aware of any upper limit to forming a black hole. But in practice, it seems to be maybe 10 billion solar masses or something like that. Billion, yeah. One of the outcomes of the modeling of this ring is that a pretty accurate estimate of the mass. They are now quoting 6.5 plus minus 0.5 billion times the mass of the sun. Yeah.
Sir, what do we understand from the picture of the black hole we got?
Okay. First of all, the fact that you're getting this ring, all right, agrees with the predictions broadly. But you don't go to all this effort and expense just to say, okay, we've got a ring and therefore we have seen a black hole. So what this collaboration has done is to model. If you look carefully on the ring, you see a brighter side, and then it becomes faint on the other side. Okay? So they have constructed a detailed model because there's a lot of other information about M87. Like this jet is supposed to be pointing at 17 degrees to the observer. Okay, then the ring of matter is perpendicular to the jet. And it's moving in this innermost stable orbit, it's moving at a decent fraction of the speed of light. So then one part is coming towards you, one part is going away from you. And that is supposed to explain why the brightness is different at different parts of the ring. So people are doing very detailed modeling. And in fact, the person whose name I mentioned, who actually visits Bangalore, he's given talks here, Ramesh Narayan, is one of the experts in modeling both the matter, the magnetic fields, the radiation around the black holes.
So my question is, can you find out wormhole with the same mechanism? Can you identify a wormhole in space with the same mechanism as we do for black holes? As much as we know, it's wormhole consists of two mouths and a tunnel, in a tunnel, and the two mouths are made up of black holes. So the matter that the black hole sucks in is, where does it go? And the black holes are identified by the same mechanism.
Okay, as far as the material outside is concerned, you had a solution with a horizon. The only properties which are being used in all this modeling are the properties of matter and light orbiting outside the horizon. So interestingly, the physics inside the horizon doesn't seem to influence what's happening outside the horizon. Okay? So, I mean, although I'm not aware of a respectable solution which has a wormhole, but even if there was one, if it looked like a black hole from far away, then a lot of what I said would still be valid. Now, what happens to the matter which goes in is this topic which is still not completely settled, or not, I would say not settled at all. Classical general relativity simply says that in a finite time it goes and hits something called singularity, and we don't know what happens after that. Pretty much like we don't know what happened before the Big Bang. It's a singularity. Mathematically, the equations just refuse to give you an answer. But then that means people don't give up, they propose other equations.
As the information says in Google or wherever you search, the matter that's sucked into the black hole goes to another universe.
That, as I said, at a speculation level, that may be interesting. But then the other end can't again be a black hole, right? Because things have to come out of it. I'm not aware of solutions of Einstein's equations which have a black hole connected to a white hole, but maybe some expert. Okay, so Bala here says no.
Thank you, sir.
The last question.
Yes, sir.
So, how is it that the supermassive black holes, they come to be at the center of galaxies and not anywhere else in the...
Okay, that's a very interesting question. First of all, the conditions for forming a black hole are the best in the center. Okay? Because it's the, let's say before you form the black hole, all galaxies have a distribution of stars which peaks. The density of stars peaks toward the center. So any gas which falls in will orbit and reach the center. And at least in the early phases of galaxies, lots of stars must have formed near the center. So already the formation could be at the center. However, your question is very interesting from the following point of view. Many galaxies have satellite galaxies around them. For example, our nearest neighbor galaxy is something called M31, Andromeda Galaxy. It has a satellite galaxy, M32. M31 has a black hole, M32 also has a black hole. These were discovered by Hubble Space Telescope. So M32 will ultimately spiral into M31, will be captured by M31. Then there is a process which actually worked out by Chandrasekhar called dynamical friction, whereby as this black hole moves through the galaxy far away, it experiences some kind of friction from the surrounding stars, and its orbit shrinks in exactly the same way that I explained, and it ends up at the center. So the center is like the ultimate graveyard, any heavy object. And this is true not only for black holes, even for a cluster of stars, the heaviest stars end up at the center.
Okay, sir. Thank you.
Suggest that we wind up this question and answer session at this point. So let's thank Professor Nityananda once again for this wonderful lecture.